então.
Só a ideia, porque as contas.
Tá. Então, você quer entender a estratégia da prova, mas se eu te contar a estratégia da prova no caso de variáveis e IDs, ou você quer que eu te conte no caso de Markov?
Sim, pode ser, mas é porque você está fazendo a conta de uma Martingale exponencial,
Sim.
coisa, mas eu não estou vendo como isso vai ajudar na probabilidade que a gente quer limitar.
Tá. Então. So, to answer a question, I will start this lecture by recalling the strategy to the proof of the large deviation. So we are talking about the symmetric exclusion process, and we start with some measure. So let's say that we fix an initial profile which I represent by rho 0. So this is the initial profile, and we start our process from a product measure associated to this initial profile. This is not very important, it's just to fix ideas. And so now we have our process, which is the empirical measure. So the empirical measure induces a measure. So if we start with this initial state with this dynamics, these two objects induce a probability on this space. So M is the space of measures which are positive, total mass bounded by 1. These are the space of trajectories. And this is, we have a measure here which I'm representing by B, P, nu, n, rho 0 dot, which can be understood that, well, the symmetric exclusion process is defined in some space. In this space, there is a measure. We indicated that the initial condition is given by this measure, and we compose that with the empirical measure in order to get a measure in that space. Okay? So now we have seen that this measure has a topology, so that this is a metric space. So we define this cohort topology in this space. And the question is, we want to estimate the probability that this trajectory, pi n, which is an element in this, belongs to some space, some set A. And what we want to prove, it's a lower bound and upper bound. So we have seen we'll take the logarithm, we'll divide that by n. And in the case of a closed set, what we'll prove, it's a bound like this. This is the minus the infimum for p belonging to A of a certain I of p. So this is our goal. And we also have a bound for open sets. Okay, so this is the goal. So the strategy will be exactly the one that we adopted to prove large deviations for IID random variables. So what I will do is I'll take this, my set A, and I will say, fine, this is equal to I'll fix a test function g. I'll define an exponential martingale. And I'll multiply that and divide that. And what is our martingale mg of t? Well, we have seen that in the context of Markov process, we have special exponential martingales. So in our case, I'll take n pi n t g t. Okay. So let me first take g as a function which does not depend on time, minus n pi n 0 g. And then I have to remove the integral of the exponential of minus n pi n s g ln, and this is multiplied by n squared, exponential pi n s g ds. So we have seen that this is a martingale. If g is, let's say, a C2 function, this will be a martingale. Okay? So now let me assume, though it's not true, that I can represent this exponential martingale by some function. Let me call that f, which depends on g. So maybe let me use a different letter. F, some function f of g. So for each g, let me assume that this is a function of pi n. Let's assume that. So you see that this is a function of pi n, this is a function of pi n. It's not clear that if this is a function of pi n, but let's assume. So I'll just replace this fg here, and I will rewrite that this is equal to the probability mu n rho 0 dot that pi n belongs to A. Then I have the exponential, let me put n here. Exponential n phi of pi, phi g of pi, and then exponential minus n f or g of pi, but let me, okay. Right? Because we just assumed that this martingale is actually a function of the empirical measure. So once we have that, I would say that, well, I know that pi belongs to A, so I will fix, so this is a martingale, I don't touch, I look at that one, so this will be bounded by the supremum for pi in A of this expression. So I will estimate this, taking into account that this is bounded by the exponential, the sup of pi in A. So remember, A, it's a subset of this set. Okay? So A, it's a set of trajectories. So it's a sup of pi in A of minus n f g of pi. And I can write that as exponential minus n infimum of pi in A of f g of pi. So this is a number now. It gets out from the expectation. This is bounded by 1. This is a martingale. This martingale at time 0. So this is 0. This cancels with that. I have an exponential. So this martingale at time 0, it's 1. So the expectation of the martingale is constant. So this is 1. And therefore, I get immediately that this probability is actually bounded by that exponential minus n infimum of f g pi. Which means that if I can, so everything is relying on this identity, right? Then, once I have that, I can just add, so I take now the logarithm here, that will cancel my exponential. I take 1 over n, that will cancel my n. And this does not depend on n anymore. So I can take the limit sup in n to say that this is bounded by minus the infimum for pi over a of f g pi. So this is what I get from this argument. Now, of course, here for each function g, I have a different martingale, so I can optimize over all g. So I can take here the infimum over all g. So with a minus sign, this becomes the minus supremum over g, infimum pi in a of f g pi. And now, if I can change the infimum and the sup, and I show you how to exchange if A is a compact set, what I will get is that this is equal to minus the infimum for pi in A of the supremum in G of f g pi. Okay? And so this is exactly what I want, and I have here a formula for I. So this is I of pi. So that's the strategy for the upper bound. Okay. Now, well, since I wrote everything here, let me complete the proof. Let me complete the proof because we computed already this martingale on Thursday. So this martingale, it's exponential n times pi nt g minus pi n0 g. And then there is this term which we computed, and it's equal to the integral from 0 to t. So we had first pi ns, the second derivative of g. So this was a linear term, and we had sorry, there is no the sum here. This is and the problem was with the nonlinear term, because we had here eta s x minus eta s x plus e square times the gradient n g at x square ds. And the problem is that, well, this is not a function of the empirical measure, so I don't have this identity. And this is exactly the problem we faced when trying to prove the hydrodynamical limit. So what did we say? Well, we say, let's try to exchange this with a function of the empirical measure. And what is the function of the empirical measure? Well, we have here a function, eta 0 minus eta e square. Okay, so this is a function, h of eta. It depends on eta 0 and eta e. Let me define h tilde alpha as the expectation of this function with respect to the grand canonical stationary state, which is the Bernoulli with parameter alpha. So that's very easy to compute. So in our case, if I compute this square, I get eta 0 square. But eta 0 square is equal to eta 0, because eta 0 takes only the value 0 and 1. And the expectation of eta 0 with respect to nu alpha, it's alpha. Then I have plus the expectation of eta e square. This is, again, expectation of eta e, which is alpha. And then I have minus 2, the expectation of eta 0, eta e. But under nu alpha, these variables are independent. So it's the product of the expectation, which is alpha squared. So this is 2 alpha, 1 minus alpha. Okay, and this is my function h tilde. And so the idea was to say that if I compare this function with h tilde of the empirical measure computed at, so I take x minus e, x plus e epsilon, I take the, and divide that by 2 epsilon. Okay? So I'm taking here the empirical average of particles. I'm looking how many particles I have in this interval. I count the number of particles. I divide that by 1 over n times 2 epsilon n. And so this gives me the average of particles in this interval. And so I'm comparing this function with this one. And let's assume that I can indeed show that this difference is very small. If I can show that this difference is very small, when I send n to infinity and epsilon to 0, this means that I can replace this function by that one. And if I can do that, now I have an expression, a martingale, which is a function of the empirical measure. So this is my, when you replace that by that, this becomes my, how I would present it, exponential n times f. Mind that now it depends on epsilon and on g. G epsilon of pi. Okay? So assume that I can replace. So now this expression minus this one, minus this one, minus the integral of, so here it will be integral from 0 to t. That becomes Riemannian sum. So I have a sum in dx, ds of this expression times the gradient of h squared. Okay? So this is my function. And therefore, by repeating this argument, if I'm able to do that, what I will get is an upper bound for compact sets in which the supremum which appears here is this expression. So I of pi will be the supremum in G of pi t G minus, okay, let me write it this way, pi 0 G minus the integral from 0 to t pi s G second minus integral from 0 to t ds, integral on the torus dx, and here okay, so let me call sigma alpha 1 minus alpha. And so what I get here, it's 2 times sigma of pi x minus epsilon x plus epsilon divided by 2 epsilon 2. So this is what we get. So this is I. Okay, so this is the bound I get from this strategy. And I forgot the g here, right? And this is times g prime squared dx. Okay, I forgot the g prime squared. Now, let's remember that pi t dx is absolutely continuous, so I can write it as utx dx, because there is no, there is at most one particle per site, so everything is absolutely continuous with respect to Lebesgue. And so if I replace now pt by this object, what I get is that this is a supremum over g, then gx utx minus u0x dx minus the integral from 0 to t ds towards dx u sx g second x, and then there is this linear term which is minus 2 times 0t ds dx. This is sigma of, I'm doing here an integral from x minus epsilon to x minus, so 1 over 2 epsilon, x minus epsilon, x plus epsilon, u s y dy, g prime x square. Okay, so this is I. And as I argued before, when epsilon goes to 0, this is converging to USX. Okay? If u were continuous, that was clear, but you can approximate any function L1 by a continuous function, and you can justify that as epsilon goes to 0, this will converge to USX. So if you remember, I can replace this function by that one if I send n to infinity first and then epsilon to 0. So I have to send epsilon to 0, and by sending epsilon to 0, this will become USX. So I will erase that and write USX. Okay? And so you have your I. So I of pi is this one. You take the supremum over all j. Mind that here you have something which is linear, right? And then minus sigma of u, a quadratic term in G. So this is almost correct. It's not totally correct because in order to get, so what I said, it's absolutely correct. But if you want to show that the upper bound coincides with the lower bound, you have to take functions g which depend on time. Okay, here I took a function which does not depend on time. If it does not depend on time, well, I get that bound. That bound, it's not good enough because to get a better bound, I have to consider functions g which depend on time. Okay. That's not a big problem because if you go back to this formula, if you allow your function g to depend on time, everything I said, it's correct, but there is an extra term, which is minus 0t and pi and s dsg ds. Okay? now, if you take a function g which depends on time, when you compute your exponential martingale, you need to add this expression. Okay? So if you go back to our proof, to the proof I gave you to show that this is an exponential martingale for g for functions which do not depend on time, if now you consider a function which do depend on time, the same proof with this extra term will show you that indeed what you have is an exponential martingale. Okay? So, and mind that this term, it's a term which is a function of the empirical measure, so there is no harm into adding it to your expression. The only difference is that you'll get here one more term. Right? So here the formula will be the same formula, but with an extra term, which, well, mind that now our function g depends on time, and you have an extra term, which is ps dsg. Okay. And this will give me an extra term in this formula. And this is the upper bound. Okay? So in order to complete the proof of this argument, I just have to justify that I can change. So questions? Okay, so let me remind you of the argument. Sure.
So why do you get an n squared in front of the rule instead of an n cubed?
Okay, so this n square comes from this generator. The generator is speed up by n squared. And here, this n, this extra n, appears here at the exponential.
Another question was, so in order for us to exchange the sup with the int, we use that we have a lower semi-continuous
Yeah.
function. So since you are taking a continuous function as f, does this mean continuous?
Yeah, so that's a good point. I need upper or lower semi-continuous functions. So look at this function, and so I needed this function to be upper semi-continuous in G. So in the variable g. So here it's linear, and here it's quadratic. So it will be it will have the upper semi-continuous. The lower, it depends if you put the minus sign or not, that you need. So and mind that if I look, so I have a function here which depends on two variables, right? This is the object which appears here. It's an object which depends on two variables and you want to exchange. So if I look at this function as a function of g for u fixed or pi fixed, I have a piece which is linear, which is fine. And then I have a piece which is convex. And this convexity will give me the continuity I need. While if I look it as a function of pi or u, I still have a piece which is linear, and then sigma, it's concave. So we have exactly what I said, that in one variable it's concave and in the other variable it's convex. And this is one reason that, the reason that you need in order to exchange sup and int. Because it's convex in one and concave in the other.
And as
Sure, sure.
So, could you give any intuition why do we choose F to be n by n keys?
Why this martingale?
Yes, because we proved that that is a martingale for any F.
Any F. Now,
We chose one specific. Why that one?
okay.
Because this is very similar to what we thought for the martingale when we were studying the hydrodynamic at least the first one, minus the first integral.
Yeah, I would say that you want something which will become a function of pi n. So what are the natural functions of pi n? These ones. So, and once I plug this function, all the other things are fixed. So what I'm saying is that this is a natural candidate. Okay, because I want these exponential martingales, as I told you, to be functions of pi n. So what's the first function of pi n that occurs to you? It's this one. So you try that one, and it works. Okay, but I can tell you at the end why these are the ones. I'll give you two reasons at the end. Any other question? But you have to remind me, otherwise I will forget. Okay, so this is a sketch of the proof. It's based on this modification, on this exchange, and what I want is explain how you formalize. Right? We have seen that the crucial point in this proof, once you have the strategy in mind, is this replacement. And so, how do you justify? This is what I wrote on Thursday. Let me call, so I fix this function g, I fix an epsilon, and I fix a delta, and I call the function the set bg is the set of all trajectories such that this difference, so the difference between this and this multiplied by that, it's small. It's smaller than delta. So this is the set of pi's such that the integral from 0 to t ds, 1 over n, the sum in x, the translation of a function v which depends on epsilon, and g of eta s. No, it doesn't depend on g, sorry. Times g prime x square, that this is bounded by delta. And what's v epsilon? V epsilon of eta, it's my function h of eta. Remind that h is this function, eta x, eta 0 minus eta e square. And I want to replace that by h tilde of pi n chi x minus epsilon x plus epsilon to epsilon. So this is my function. This is v. This is the v here, and I'm translating that by x, so that will be h applied at tau x, and okay, and this is also translated by x. So I want just between minus epsilon and epsilon. Okay, and then I translate by x. So let me define this is a set of trajectories, and as we have seen, what we will do is that we will intersect this set with this set. So we will write that this probability, it's less or equal than the probability that pi n pi belongs to A intersection B G epsilon delta plus pi p belongs to the complement. And so the probability that pi n belongs to A is bounded by that. So if I take now the log 1 over n limit sup, we have seen that once we have a sum, this limit sup, it's bounded by the maximums. So this will be bound, this is bound. So the limit sup, it's bounded by the maximum of the limit sups. So we have one limit sup, 1 over n log this one with B, and the other one intersection A, and the other one complement. Okay? Now, if I want to show that this one, that the maximum is equal to this one, I have to prove that this one is very small, that this one is minus infinity. So what I need to prove is that this, so mind that I have here a complement, right? I have to show that this is equal, when I send epsilon to 0, that this will converge to minus infinity, and this for all g and all delta. Okay? Because if I can prove that for all g and for all delta, as epsilon tends to 0, this goes to minus infinity, then it's clear that the maximum is given by that. Okay, so I can just ignore that and get that actually that limit sup is bounded by this one. But on the set B here, this difference, this expression, it's bounded by delta, which means that the difference between my third line and the fourth line, it's bounded by delta. Right? So I will be able to replace that by that at the cost of delta. So this cost of delta is actually just changing my f by delta. So what I would have here, it's not this expression, but this expression plus delta. Right? Because when I exchange the sum with the integral, I lost a factor delta, because this is telling me that, well, the third line, which is this one, and the fourth line, which is the one with that, they are not equal, but the difference is bounded by delta. So since I need bounds in this argument, right, I'm always talking about upper bounds, well, this expression will be bounded on the set B by the same expression in which I replace this by this plus delta. So what I will get here, it's not this function, but n times this function plus delta. Right? So this is just adding a delta to I in all this argument, but that's fine because this is true for any delta. So after sending n to infinity and epsilon to 0, I can send delta to 0, and this delta will disappear. Okay? So the crucial point here is to prove that this limit soup, as n goes to infinity and then epsilon goes to 0, goes to minus infinity. So this is for the upper bound. Right? Questions about the proof, the argument? Okay, so what remains here is to show this, and this is what I'll do now. So I will erase everything. So here is my definition of my set and my claim. So it's theorem. And this is what's called the super exponential, because it's super exponential, right? Because so we are showing that this limit, it's equal to a constant epsilon, which converges to minus infinity, which means that this probability, it's exponential minus c epsilon n. So it's more than exponentially small. Because, well, this c epsilon is going to infinity. This means that it's more than exponential. You have exponential minus n with a constant which is increasing to plus infinity. So it's super exponentially small. So it's called the super exponential estimate. And what I want to prove is that the limit, as epsilon goes to 0, the limit sup as n tends to infinity of 1 over n log the probability u n rho 0 that pi belongs to b, what I call g epsilon delta, it's equal to minus infinity. And this is for all g and for all delta. Right? Questions? So this is the central point. Fine. So let's see what we want to prove. We want to estimate the probability that, okay, and this is the complement, right? I want this to be larger than delta. So I have this absolute value. If the absolute value is larger than delta, this means either the expression is larger than delta or minus the expression it's larger than delta. Then by using the same argument that the limit sup, well, so I have the probability of two events, right? That this is larger than delta or that minus this is larger than delta. So the probability of two events, I bound that by the sum of the probabilities, and now I use this bound to show that, well, I have the maximum. So it's enough to prove that both go to minus infinity. So I can just disregard this absolute value and eventually replace this expression with a minus sign here. But okay, this minus sign, it's you'll see it's irrelevant. So what I need to prove is that this expression that what I want, it's the same expression over there, but without the absolute value. And let me replace g prime square by h. Okay, so I'm estimating that this is larger than delta. So this is what I'll prove, that it's super exponentially small. And mind that, well, if you want a minus sign here, it's just to consider that instead of h, you have minus h. All right? So let's use an exponential Chebyshev estimate. So I'll multiply that by n, and I'll fix a positive, and I will multiply that by a, and I will use the exponential Chebyshev estimate in order to estimate that. So I multiply that by an. So here I get minus exponential a delta n, expectation of the exponential. So I multiply that by an. So the n goes away, and I have a 0t 1 over n x tau x v epsilon g epsilon eta h. All right, so this is what I get. No? So if I take the log, divide that by n, and send it to infinity, what I get is that this is bounded by minus a plus the limit sup of this expression. Right, so if I take the limit sup in n, and the limit in epsilon, what I get is that this expression is bounded by limit epsilon. Okay? So if I show that this is equal to 0, it's bounded by 0, for all a, I'm in business because this is bounded by 0, so this will be bounded by minus a, and therefore I send a to infinity, and that's all. So I just have to show that the second term is bounded by 0. So let's look at the second term. We have a formula for that. Right? We have seen that this expectation, remember that this expectation is written as the expectation with respect to a measure mu of exponential 0t of some function w eta s ds. Okay, and this we wrote as pt w 1, 1 with respect to this measure mu, and we proved that this is bounded by the exponential t times lambda, where lambda it's the supremum of W f square minus n square df. Okay, so this is what we proved. This is the Feynman-Katz bound. So this is exactly what we have here with W is okay, and you allow me to write n. This n is not there anymore because we multiplied our expression by a times n. So this n gets away. Okay. So we have this expression here, which is W, and therefore, by the Feynman-Katz formula, we know that this limit, it's bounded by, we have t. So I'm taking here, we have this expectation, it's equal to the exponential. When I take the log, this exponential gets away. So it's bounded by the limit in epsilon, the limit sup in n, 1 over n, lambda. Okay, so now let's see what is 1 over n lambda. So 1 over n lambda, it's equal to 1 over n, the sup in all f, which has L2 norm equal to 1, of W. W is that expression. So it's A, sum in x, tau x v epsilon of eta, hx f squared d nu alpha minus n squared df. And this expression, we already faced that expression. So let me put the 1 over n inside. Remember that this is the Dirichlet form, so this is minus n f lf. And we already estimate this expression by a long computation. Now let me recall what is V. Okay, V I erased, but V epsilon of eta was eta 0 minus eta e square minus 2 times sigma of the average. So let me write it. In this way. So remember that the expectation of this function was equal to 2 times h1 minus h, and sigma it's alpha 1 minus alpha, and sigma of alpha it's that. It's alpha 1 minus alpha. So let me expand that, that difference. So this is eta 0 plus eta e minus 2 eta 0 eta e minus 2 times sigma, it's alpha 1 minus alpha, so this is 1, 2 epsilon n eta y, and 1 minus the same thing. So there are linear terms, and these ones are easy. So I will compare the linear with the linear and the quadratic with the quadratic. So this difference so I can rewrite this difference taking the 1, which will give me a linear term. So I have to compare eta 0 plus eta e minus 2 times 1 over 2 epsilon n so this is one term which I need to estimate, and the other estimate, it's this one minus the square. So the other one, it's minus 2 times eta 0 eta e minus 1 over 2 epsilon n. Okay, so I wrote this difference in this way. So I claim that this one is very easy to estimate because it's just an integration by parts. Questions? So let's see that first this one. So let's recall what's written here. We have A divided by N. And let me compare eta 0 with this. The comparison between eta e and this is exactly the same. So what I am doing is I'm translating this expression by x. So here what I get is hx, x, eta x minus this expression, minus 1 over 2 epsilon n, y less or equal than epsilon, eta x plus y. Okay, so this is the first term, eta 0 minus this average. Right? But here I just want to change the order of summation to get that this is A over N, the sum in x, eta x, hx, minus 1 over 2 epsilon n. So I'm changing xy, x plus y, I'm calling that x. And so x becomes x minus y. So this is hx minus y for y less than epsilon. But if I change now minus y by plus y, I get exactly the same thing. And now I can here h is a smooth function. So what you see, I can do an expansion. I have hx plus y minus hx. Here I'm summing over 2 epsilon n terms, which are exactly the number of terms I have here. So this is equal of A over n, summation in x, eta x, and here I have 1 over 2 epsilon n, y less than epsilon, hx plus y minus hx. Okay? And, well, let's say that h, it's Lipschitz, it's C2. So in particular, it's Lipschitz. That makes this difference bounded by a constant times y. And y, it's bounded by epsilon. So this is bounded by constant times epsilon. Here it's an average, so this is an average, so it's still bounded by epsilon, and it's bounded by 1. I have here an average, so everything here is bounded by a constant times epsilon times a. So this difference of this term, or of this term and this one, the contribution of these terms are bounded by constant times epsilon times a. Therefore, this is uniform in n. So when I send n to infinity and then epsilon to 0, this goes to 0 for all a. So this term really has, it's easy to deal. The linear terms are simple. So I really, I don't need to, well, these two terms and these one are simple. The problem is to estimate the quadratic terms. Okay, you agree with that? So linear are simple, problem are quadratic. Fine. So in this sum, what's really the problem is to estimate I have hx, and now what I have here, it's eta 0, or eta x plus e, minus 2 epsilon n, y smaller than epsilon, eta x plus y square. F of eta square d nu alpha, and this minus n over the Dirichlet form. So this is what I need to estimate. I need to show that as I send n to infinity and then epsilon to 0, this is bounded by 0. Okay?
Why did you change the measure when you revised the exponential from that one, from that step to that one? Why did you change to a constant profile on the measure?
Okay, because this is I want to show that this is goes to minus infinity. So this measure, which I'm starting with, of some set A, I can rewrite it as, let's say here with the profile, here constant measure. Just by writing the Radon-Nikodym derivative of this one with respect to this one. Okay? If you compute this expression, the Radon-Nikodym derivative, you show that it's bounded by a constant times n. Then if you take the log divided by n, this is a constant, but the other one is going to minus infinity, so it kills. So when you want to prove super exponential estimate, you can always assume that you're starting from a flat profile, or the profile you want. But that's a good point. I didn't say it, I omitted it. Okay, so going back, what I need to estimate is this term, because the linear terms are easy. And this one we already proved. We already estimate this term. This expression is exactly the one we faced when proving the hydrodynamical limit. Okay, so, and if you want to look exactly the same, what I can do is to put this a in front of everything, and then I have here a. And if we recall, what we proved is that this limit, as n goes to infinity, and then epsilon goes to 0, it's bounded by 0 for all a. In the proof of the hydrodynamical limit, we had the same expression, but instead of a, we had a delta here. So actually, we already proved that. And therefore, this completes the proof of the super exponential estimate. So the proof I proposed to you when we deduced the hydrodynamical limits of these exclusion process in which the speed at which exchange depends on the neighbors, well, I presented that proof because it applies also for this super exponential estimate. Okay, maybe you're not convinced, but if you just write down this equation and you go back to my lecture on the hydrodynamical limit, you'll see that this is exactly the expression which appears there, and we proved that this is indeed less or equal than 0 for all a when you send n to infinity and then epsilon to 0, because we started exchanging here. I fixed an x, and I compare eta x plus e with this average. I start to exchange, and this is exactly, this argument shows that this expression vanishes in the limit. Okay? And so with that, we get the upper bound. Okay, well, there are some details which I am omitting, because once you replace this expression by this one, well, you still have to send epsilon to 0, delta to 0. But these are technical points. This is the crucial part of the proof. So that gives you the bound for compact sets. Now, to extend this bound from compact to closed, you have to find the sequence of compact sets which goes to minus infinity as well. Okay. And this can be done, but I won't present it. It's quite technical. But you construct explicitly a set of compact, a sequence of compact sets which has this property. Okay? But to go from compact to closed, you still need an argument, but it's quite technical, so I will not present it here. So this completes the proof of the upper bound. Questions? Okay. So that's the upper bound. Now let's go to the lower bound. So here, we introduce some perturbation, right? These exponential martingales, if you fix a function g, now let's say that depends on time and space, and that it's smooth. So it's very smooth, C2. Then I propose to consider a martingale, which depends on g, which is the martingale I wrote, the exponential, and pi n t gt minus what we need to make this a martingale. So this is a martingale. So with this martingale, I can define a measure, a new measure. This measure p, j, exactly as we did in the case of the IID random variables, will be defined by taking the original measure and putting this martingale, this exponential martingale. Okay, so that this defines a new measure pj, which depends for each g, that each smooth function g you give me, I can define a new measure, exactly as we did for IID random variables. So if you want to compute the probability of an event A for this measure, this is just the probability of chi A times this exponential martingale. This exponential martingale is nothing more than the Radon-Nikodym derivative of the measure pj with respect to the measure p. Okay. Reduced to the sigma algebra of all events before t. Okay. So this is a measure, a new measure. And we have seen that it's very important in order to prove the lower bound to prove a law of large number under this measure. For the IID random variables, we proved that the average was converging almost surely to a new constant, m of theta. So for each theta, we had a new measure, and which had an average, m theta, and we proved the law of large number. We proved that xn bar was converging to m theta. Why? Because, well, this measure p theta was very simple. It was just, again, a sequence of IID Bernoulli, but with a different parameter. Okay, here, apparently, we are in a completely new world because we are now, this is a function. For each function, which depends on time and space, we have a new measure. So we have to understand what is this measure. And to understand this measure, we have to understand what is these martingales. Okay, but we have all tools we need here in order to understand this measure. So let's say that we fix an interval 0t. So this, let me take this exponential martingale up to time t. And I want to understand what is this measure pja. So this is a measure in the 0t m, or the 0t in our space 0, 1, lambda n. And in order to understand what is this measure, what I want to do is to compute. So I'm fixing a function g. This is fixed once for all, right? So I'm taking the expectation with respect to this new measure of f of eta t. That's fine. And I want to compute that. Because if I can compute that, then I know what is this measure. So by definition, this is the expectation with respect to the original process of n eta t m g t. Okay, so this is the definition of my new measure. Measure of any set, it's given by this form. And here it's an expectation, right? Okay. So this depends on time up to time t. So let me first take the conditional expectation of this expression with respect to ft. So this one, it's measurable. So what it gets out from the conditional expectation, and what I get is the conditional expectation of this martingale given time t. This is a martingale, so its conditional expectation is equal to itself at time t. So I can replace here the capital T by small t with this argument. Fine. Now let me recall you what is this martingale. Well, it has an explicit formula. This is exponential n times g p t. And let me take a g which does not depend on time just to avoid one term, just to have a formula slightly smaller. But otherwise you add one integral. Okay, so this is the martingale, and this generated speed up by n squared. Okay? Now, this formula, you have seen it before. Let me call this expression W of eta s. This is a constant, so it gets out. Depends only on what happens at time 0. And what remains is the expectation of the exponential 0t w of eta s, ds, which is everything here, right? Including the minus and the n squared. And times f of eta t exponential n g pt. Okay. Didn't do anything. And now you recognize here a new semigroup ptw applied to the function f exponential. And the initial term, right, which I didn't write. Right? So this exponential martingale, it's creating a new semigroup, PTW. But now I'm applying this semigroup in the function f exponential. So this means that if I take the time derivative of PTW applied to the exponential f exponential n g pi, we have seen that this is n squared L plus W applied to this function f exponential n g p. So I'm taking this and saying that I'm taking it at time t equal to 0. Okay, so this is n squared times L applied to the function f exponential. Let me write this. This is gx eta x. So this is n square L applied to that, and then plus w. W is the function minus n square exponential minus n g pi L of exponential n g w. So this is the function w, which is multiplying f exponential n g pi. So this exponential, this is just a multiplication, right? L is applied to this function. So this is just a multiplication, so it gets out with this one, and here it's the formula. The formula is, this is equal to n squared, L applied to f exponential gx eta x minus f L applied to E sum gx eta x. Okay. But L, remember, it's an exchange. We are in the exclusion process. So this is, and let me write this function as R. So this is n squared, sum of x, then f times r, sigma x, x plus e of eta minus f times r at eta. So this is the first contribution, minus f of eta, and then L applied to R. R sigma x, x plus e minus R of eta. Okay, so this is what we get. So you see that this minus FR will cancel with this term. And what we get is that this is n squared, sum of x, r sigma x, x plus e of eta, f of sigma x, x plus e eta, minus f of eta. Is that correct? Looks like. Yeah. There's a one which is missing. No, because I forgot the term, this term. Okay, this term it's multiplying every one. This is the r which is missing. So I forgot here to put, when I'm taking this derivative, I'm always forgetting this term. So there is here a minus which is multiplying everything, which is minus this n p g0. Okay, so this term it's multiplying every one. So it will appear here as multiplying this term and minus n p. Okay, this term, which is here, I forgot to keep track of it. So it doesn't depend on anything, right? So it's just a multiplicative constant. And since I called this is r, this is 1 over r. Okay? In my computation, I called r this function, but this is exactly r, but with a minus sign. So this is 1 over r. So what we have here in my computation, it's r of eta. Right? Or should I go back to the computation? Are you lost, or you agree with that? Okay, I've just left this term on my way. So if I get it back, I'm just multiplying every expression by this one, and I defined r as this exponential. So you see that what's appearing here, it's exactly this exponential, but with a minus sign, so it's 1 over r. So what I get here, it's the formula I was looking at, I was wishing, it's this one. So now, let's recall what r is. R is this function. So let me compute this ratio. So r sigma x plus e of eta divided by r of eta, it's equal, so r is this function, sum over y of gy, then sigma x plus e, eta of y, and this is divided by the same expression, so it's minus eta of y. And we computed this expression many, many times. It's equal to minus gx plus e minus gx, eta x plus e minus eta x. And this is this ratio. So this is equal to n squared, the exponential of minus g x plus e minus g of x, eta x plus e minus eta of x, so we get that this expectation, it's a new Markov process. When I compute it, its derivative, so I computed this at time t. I took the derivative at time 0. So when I take the derivative at time 0, I get the generator. So I computed the generator. And the generator, it's this expression. So let's understand what it means. It means that for this process, this new process, I'm exchanging what happens at x and x plus e, not at rate 1, but at a rate which depends now on this function g. If I have a particle at x and no particle at x plus e, which means that I will jump from x to x plus e, so this is minus 1, this is 1, and so the rate will be exponential times this difference, which is a gradient. You see, this is the derivative of g divided by n. So this is a term of order 1 over n. So this means that I'm jumping from x to x plus e at a rate which is exponential minus 1 over n g prime of x. Let's see if I have the minus. So this is 1, this is 0, no plus. Okay, so instead of jumping at rate 1, now I'm jumping at a rate 1 plus a correction of order 1 over n, 1 over n g prime. And I jump from x plus e to x. This means that I have a particle at x plus e, no particle at x, so this difference is 1, and so I get minus the derivative. So this is exponential minus 1 over n g prime of x. Which means that now this dynamics, it's not symmetric anymore, but it is weakly asymmetric. Because instead of jumping with rate 1 to the right and 1 to the left, I'm jumping to the right with rate 1 plus 1 over n g prime. So if g it's increasing, g prime it's positive, which means that I'm jumping with a rate which is 1 plus a constant positive divided by n to the right, and to the left I'm jumping with 1 minus this constant divided by n. So the process is asymmetric, it's not symmetric anymore, but it's weakly asymmetric because the rate is 1 plus 1 over n. Okay. So this means that when I fix this function g, and I introduce this martingale is changing the dynamics. How is it changing the dynamics? By introducing an external drift. It's like now that you have an external drift which is moving the particles to the right more than to the left. Okay, well, in the points in which g prime is positive. If g prime is negative, it's the opposite. Right, so we have to prove. Okay, now we know what this martingale is doing. It's changing the dynamics. How is it changing? Well, by changing the generator to that one. So instead of having 1, now we have this exponential. Okay. So we have to study this new dynamics, this new evolution. This is point 1. So we have to prove a law of large number for this new dynamics. What happens with the empirical measure when instead of evolving according to an exclusion, you evolve according to this generator? So that's the first question, which we will answer. Then there is a second question, which is, and this answer to your question more or less, it's what are we trying to prove? What we are trying to estimate, it is what is the probability that my trajectory, my empirical density, will follow a trajectory utx dx in the time interval 0t. 0 capital T. Right? When we were studying the IID random variable, our question was, I want to estimate what is the probability that xn bar will be close to some beta, or that this difference will be smaller than some epsilon. This was the question, right? Estimate this probability. What is the equivalent of estimating this neighborhood? Well, now you have a trajectory. You take a tube along this trajectory, and you want to estimate the probability that your trajectory will remain in this tube, which means, in order more formally maybe, is to say, well, what is the probability that the supremum between pi nt and u tx dx, that this supremum will be less or equal than some delta. Okay, so you fix a tube around ut, and you ask, what is this probability? So what did we do? Well, given this beta, given that beta, I constructed a measure, p of theta, which turned beta a typical value. Okay? Remember, for theta, I construct a measure. For that measure, I had an expectation, an average, equal to m theta, and then I chose theta, for which m theta is equal to beta. This is what I did. Now I give you u. I give you a trajectory u. Then the same question, well, if I translate this question to this new context, is the following. Find me a function g which turns u a typical path. Okay? I know that if u is the solution of the heat equation, then I take g equal to 0. But now if I tell you, if I give you some u, some other u, well, tell me what is the g which will turn this path, this trajectory, a typical one. Okay? Fine. So the answer is the following. And this is what we will do tomorrow. The answer for my first question is, which is, let's consider this dynamics. What is the hydrodynamic equation? How the empirical measure evolved? I'll tell you. The equation was dtu equal to Laplacian u. Okay? So let me write this 1 over exponential 1 over n as 1 plus 1 over n g prime of x. Okay? So this g prime creates a current, and this will reflect in this equation by a new term, which is minus 2 times gradient of sigma of u, gradient h, gradient g. Okay? So this perturbation will create a current. So, and then, well, with the same u0, u rho 0. So this is the hydrodynamic equation. So it's not heat equation anymore. It's a heat equation with, so you see that you get a first order derivative expression in u here. G, it's fixed, is the function you introduced. So that's fixed, but you get this derivative of sigma of u. Okay? And maybe Okay, maybe I'll do that tomorrow to show you. I'll just write down the martingale. Okay, so you write down, if you want to show that the hydrodynamic equation is this one, take a test function h, write the martingale, assume that you can exchange, that you can replace functions by these functions of the empirical measure, as we did today, see what you get, and what you get is that. Then you have to prove, but you just follow the method I proposed to have a rigorous proof of this result. Okay, so the second question, it's you take your u, right? Now what you do? Well, u is now your trajectory, and you want to find g. What I tell you is that, well, if I can solve this equation for g, now I look at this equation as an equation for g. If I can solve this equation as an equation of g, then I have the solution. Because if u now it's what I know, I solve this equation in g, I get a g, I consider this perturbation. This perturbation will tell me that u solves this equation, but okay, that's fine. So maybe I'm not clear. Now, suppose that you give me a trajectory u, which is very nice. Okay, fine. You gave me u. Now, I look at this equation, but I consider that this is an equation in terms of g. So I fixed, so you see that for this is an equation in which I have essentially a Laplace equation in g. So it's an elliptic equation for g. Let's say that I can solve this elliptic equation in g and get a solution. So g. Now I take this solution and I consider this dynamics, P of g. Okay. Now under P of g, by this theorem, I know that the empirical measure converge to some function Vtx dx. And what is Vtx dx? Well, it's the solution of the hydrodynamic equation. So dtv, it's equal to Laplacian v minus 2 times gradient sigma of v, gradient of g, with the initial condition I fixed. Well, but this equation is exactly this one, which means that v, it's actually equal to u. So I created a dynamics for which u, it's the typical path. Okay? And this will allow us to prove the lower bound of t. Of course, it's not always possible to solve this equation. It's only because it's only possible to solve this equation, it's u, it's very smooth. So we will do that for u very smooth, and then we will approximate smooth paths by any path by smooth paths. But this is the idea. So questions? Fine, if not, so let's stop here. And tomorrow it will be the last lecture of this course, and we'll prove the lower bound.